I was not too terribly thrilled with the scores. I want to say the average score was around 63 or 62. So I got to thinking maybe I was the problem. Did I not present the material in a way that got across to you all? And so I was going to go through the quiz, and I know you haven't taken it yet, but what I was going to do is go through the quiz, answer any questions, and I made up a alternate quiz that you can take if you wish on Wednesday. Get to hopefully the material will sink in, and you can redeem yourselves on Wednesday, and I can redeem myself today. But all right, first question. Draw the symbol and state table for the AND gate. Oh, one thing that I noticed on there was lack of precision. In engineering and computer science, there you go. In engineering and computer science, you have to be precise. Computers don't know what you're thinking. They can't say, oh, he means this, or she meant that, or whatever. That doesn't work with computers. They do exactly what you tell them to do, whether it's right or wrong. So you have to look at the precise wording of questions and be precise. So the first two questions were drawing symbols and state tables. The AND gate is that symbol there, as opposed to the NAND gate, which has the bubble on the output. That bubble means that the output is inverted. The symbol is otherwise the same as the AND gate, just the output is inverted. So the state table for the AND gate is like so, where both A and B are high, the output is high. The NAND gate is just the opposite of that, because the output is inverted, because it has that little bubble. So it's high, 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 and low when both inputs are high. Now the second question, now the first question most everybody got right. The second question they got, it messed people up sometimes in some instances, because they thought it was a NOT gate. and did the symbol for the inverter. Other people took the OR gate and put an inverter after it, which has the same state table, but is not the same symbol. So an OR gate is like so, and the NOR gate is the same symbol, but with the inverting bubble on the output. So the state table, when either or A and B, either A or B are high, or both are high, the output is high. And the NOR, because it has the inverting bubble, is the inverse of that. If either A or B are high, the output is low. If they're both low, the output is high. But you have to look at the question and be precise. Exactly what the question asked for. Or in the case of getting out into the working world, what do the requirements need? You have to be precise. You can't say, oh, he probably meant this, or the computer will know what I mean, or whatever. It doesn't work that way. At least not yet. So that basically covers the first two questions. Now, the third question was to create a schematic diagram for the expression out equals the quantity A and B plus B naught C. So you do the order of operations. Parentheses first. Then knots. Then ands. Then ors. So we have two parentheses here. And you start from the left and you work your way right. You have three inputs, A, B, and C. A and B are ANDed together. in the first parentheses. B is inverted in the second parentheses and ANDed with C. And then these two are ORed together. The last operation outside the parentheses. The state table for this is going to have 8 possible combinations. I'm going to go ahead and use zeros and ones. And it's a matter of tracking through the circuit to see what combinations work and yield a output of 1 or high. So A ANDed with B with 0, 0 would be 0. B naught ANDed with C would be 0 as well. Both of those being 0 for the OR gate would lead to a 0 on the out. Again, 0 and 0 for A and B would lead to a 0 here, but it would and lead to a 1 here. And C would be a 1, which would be a 1 for the AND out, and 1, 0, 1 for the OR would lead to a 1. This is going to be 0, 0 again, 0 here, 0 here, 0 out here. 0 here, 0 and 1 lead to a 0 here. 0 and 1 would lead to a 0 here, should lead to a 0 out there. 0 or a 1 and 0 would lead to a 0 here. 0 would lead to a 1 here, and a 0 here would lead to a 0 here, and 2 zeros ORed together would be 0. And likewise, you'll find that the last 3 are 1s, because A is 1, B is 1, that leads to a 1 to the OR gate, and B is 0, and a 1 to the AND gate, with a 1 from the C would lead to a 1 to the OR gate, etc. So that's where you would get the state table. All right. Now, 5, create a Boolean expression for the circuit with the following state table. All right. Now, when you're going from a state table to a diagram, you identify the rows in the state table that have a 1 as an output. And then you make an expression, an AND expression, that yields that 1 output. An AND expression that has all 3 inputs in it. So the first row, there A, B, C, 0, 0, 0, and can only be ANDed together. They could only be a 1 if all the inputs are 1. So since all the inputs are 0, you would invert them all. Now that is not the same as or it's not the same. These invert the inputs to the AND gate. These invert the output of the AND gate. So there is a difference. The second row to have a 1 output is 0, 1, 1. Now you got 2 of them that are 1s, so those will work. But the A needs to be inverted to be a 1 to make the output of the AND expression 1. So it would be A, B, A prime, B, C. And the final line is, with a 1 output, is 1, 1, 0. Again, the A and the B are fine the way they are. The C needs to be inverted. And then you OR these together to be A prime, B prime, C prime, plus A prime, B, C, plus A, B, C prime. That's your output. That's your total expression. But you only need to worry about the lines that have a 1 for an output. And then this is called the sum of products. All right. Then to make a schematic for the expression, all the inputs have at some point inverters on them. A in the first 2, B on the first one, and C on the first and last one. So you have your inputs with inverters. And given that you're drawing these by hand, it's okay to have them a little messy. But you would have a 3-input AND gate for the first expression, which is A naught, B naught, and C naught. Okay? For the second AND expression, you would have A naught, B, and C. And finally, the third AND expression, A, B, and C. I'm sorry, C naught. And then these all three would go into a 3-input OR gate to be outputted. But you see how I did the order of operations? I did the inverters all first, then the ANDs, then the ORs. Kind of like the minus sign on a number. Then you do multiplication and division first, and then you do your adding and subtracting.
Off the inverters or off the first?
Which these, yeah, these are connected to the inverters.
I'm saying the top line. It's not going to the inverter.
This one? Oh, that's your regular A input. That's going to the, for example, to this last AND gate here. It's going in its regular form without being inverted. Likewise, the B goes to that as well, but the C inverted goes to that one. That's this expression right here. That's this AND expression right there. All right. Now this was a little bit sloppy and all that sort of stuff. You could draw this on a computer CAD program much more clean and all that sort of thing. But for the test, I'm not going to judge on prettiness. But we'll get to how to simplify the expression in later classes. We'll use Boolean algebra to simplify this. Yeah. And the last one, this one, I admit, messed up a lot of folks. Draw the schematic for an XOR gate using only AND, OR, and inverter gates. I did not do this in class. Most people, or a good chunk of you, did the NAND implementation, but the instructions specifically stated using the AND, OR, and inverter gates. So if you look at an XOR state table, you should be able to create a diagram that has the same functionality. So the state table for the XOR is like so. Now, there are several different ways that this can be done. One way is to look at it like number 6. Take the terms that yield a 1 and do those. So it would be B and not A. And the second line that has a 1 as an output is A and not B. And then OR them together. No inverter there. That is one way to do it. And some folks did do it that way. Another way to look at it is it's kind of similar to the OR gate. So you can do A or B. Okay. But that would, you have a 1 in this position, which is A and B inverted. So it would be A, B, ANDed together, inverted, and that through an AND gate. So it would read A or B and not A and B. See how that, I see some questioning looks. Okay, A or B would yield 0, 1, 1, 1, right? As the outputs. Here you have 0, 0, 0, 1 inverted, so it would be 1, 1, 1, 1. I'm sorry, 1, 1, 1, 0. And then you AND these two together, this one and this one, and that would yield 0, 1, 1, 0. You use this to take away the undesirable outputs. You AND it with an invert of what you're wanting to take out. Okay. The third way to look at this one is to do the NAND implementation like a lot of folks did, where you have the A, B, okay, start with that. But the question asked for only and, ors, and nots, and inverters. Okay, so to redo this with inverters, you would change all the NAND gates to AND gates, and put inverters after them. And then make NAND gates out of AND gates and inverters. Yeah.
I don't know if this is the same question. I don't see how the outputs are like that for the X. But I understand the more are it's just the or like written.
Yeah.
But I don't understand.
Why this combination makes an XOR? It's the XOR is actually short for exclusive OR. It's exclusively OR, not AND. So if one or 0 1 or 1 0 would yield a 1. 1 1 is an AND, not an OR. So it's exclusive OR. It's just abbreviated XOR. Likewise, the XNOR is exclusively NOR, not OR. So it's the invert of this, which is that. That's for the XNOR. Yeah. I'm sorry?
The fourth one.
The fourth one, what?
Fourth one.
Fourth way, let's see.
Use prompts to start.
Oh.
If I got it wrong, then I'll wish.
Well, you used a NAND gate.
So same thing. You just didn't explain it, so I wasn't sure if it was. I'm not sure. We can look at that on the board here. Let's see here. It was A, B, A prime B. All right. NANDed together you had, right? All right. And what's the second group of B prime A? And that was ANDed together, right? And then ORed. All right.
Well, that would be right, except that this would have to be a AND gate, not a NAND gate. And that was similar to the first solution I gave, where you have an inverter here and an inverter here. And just these are regular inputs. Same thing.
Those are a bunch of ways to get it.
There's a bunch of ways to get it. It's just that, we can, when you look at the actual implementation in a circuit, you want to use as few gates and therefore transistors as possible for cost and speed reasons. And we'll get into gate minimization and all that sort of stuff. Basically, that's the next section of the semester. So we'll start getting into gate minimization and that sort of thing. There is what you call a propagation delay. That if you look up in the data sheets, you'll see a gate has a propagation delay. What are we looking at? Okay. So say you have a propagation delay of 20 nanoseconds per gate, which is kind of slow, but not unheard of. You'd have 20 here, 20 here, and 20 here for a 60 nanosecond delay between valid inputs and a valid output. Basically, there's no real way to do the XOR gate without a three-step process. So you're going to look at, whatever the propagation delay is for each gate, added up 3 times, and that's what you're going to get. But we'll see later on that there are different ways to minimize the number of gates used and therefore minimize the propagation delay and therefore speeding up the process. But that about covers the quiz. We got about 5 minutes left. Is there any questions about the quiz? Yeah. Mm-hmm. Okay. Unfortunately, schematics do get larger and confusing. But I did my best to interpret what everybody had and that sort of thing. But there are several ways of doing that. I did on the board when I did it. I used 3 input AND gates. Some people used 2 AND gates linked together to accomplish the same thing. That sort of thing. And I gave equal credit for both of those. Is there any more questions? Yeah. Yes. Basically, I took the same questions and changed them a bit so they're different answers, but the same structure, the same concepts are going to be on the makeup quiz. So Wednesday makeup quiz. If you're satisfied with your grade, don't worry about showing up. I'll just mark everybody as present and go from there. Yeah. You'd keep the higher grade. You'd keep the higher of the 2 grades. Yeah. So I'm not going to change out a 100 for a 79. That would just be rude. But yeah, I'll give you the higher of the two scores, and that sort of thing. So, all right. Well, I guess that'll about wrap it up for the day. I'll see you Wednesday if you choose to. Have a good afternoon.